Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today we have Pu-Ting Yu, who is a PhD student under Chris Feil at Georgia Tech. We are happy to have him here today to tell us about Convergence of Frame Series. Take it away, Pu-Ting.
Okay, thanks for the introduction, and it's really my pleasure to give this talk here. And today we will talk about the topic, convergence of frame series, which is one of my joint work with my advisor, Dr. Christopher Heil. And today's talk will be organized in the following way. So in the first section, of course, we will introduce some notations and definitions, and of course, and some fundamental results we will need for this talk. And then we'll briefly talk about the motivation behind this research. And then the second section is about the main topic of today's talk. We will talk about unconditional convergence of frame series. And then we'll move on and close today's talk by discussing the existence of absolutely convergent frames, and also discuss why we are interested in the existence of such frames. Okay, so let's get started. So essentially, today's talk will be revolving around unconditional convergence and frames. So let me first introduce what unconditional convergence and the frames are. Okay, so throughout this talk, we will use H to denote a separable infinite dimensional Hilbert space equipped with inner product. And let Xn be a sequence in H, then we say the sum of Xn converges unconditionally if the sum of X sigma of n converges in the norm of H for every permutation sigma of the natural number. And otherwise, we would just say this infinite sum converges conditionally. And we say a sequence Xn in H is a frame for H if there exist some positive numbers a less than or equal to b, such that the following inequality holds. And we call this inequality the frame inequality. And we say Xn is a Basel sequence if the upper inequality holds. So let me say something about this definition. So one nice thing about this inequality is that this inequality is not order sensitive, in the sense that even if we permute the order of Xn, then the sequence remains a frame. And the second good thing about this inequality is that it endows the sequence itself some basis-like properties, and we will explain more on what we meant by basis-like property. Okay, so here we go. So this is exactly what we meant by basis-like property. So assume that Xn is a frame for H, then we know there exists some sequences Yn and Zn such that every X in H can be expressed as the sum of Xn multiplied by the inner product of X and the Yn. And also, we can write X as the sum of Zn multiplied by the inner product of X and Xn, and where these two sums converge in the norm of H. And we call these two expressions the reconstruction formula of X. So now, although you can see that in the definition of frame, that frame inequality is not order sensitive, but here we really have to specify what order we have to use, because these two sums at first involves the sum of infinite many terms, and the second, these two sums may only just converge conditionally. So if these two sums do not converge unconditionally, then it means we may lose these nice sequences Yn and Zn when we permute the order of Xn. So let's see some example. So let En be an orthogonal basis for H, then we can consider the frame where we duplicate E1 3 times and E2 twice, En twice, and En twice, and so on. So by the definition of frame, we can see that this sequence is a frame with upper frame bound 3 and the lower frame bound 2. So this is a frame. But the thing is, how should we order this frame? So perhaps the most straightforward order is just to let Xn be E1, 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 E2, E2, and so on. And then based on the nice property given by the frame inequality, we know this is just some sequence Yn such that the reconstruction formula X equals to the sum of Xn multiplied by the inner product of x and the yn holds, and this sum converges in the norm of H. But this sequence yn can be order sensitive in the sense that there exists some permutation sigma of natural number such that the sum equals to x equals to the sum of x sigma of n multiplied by the inner product of x and y sigma n does not hold for every x in H. And we will talk about more on this counter example later, where we cannot really permute the order of xn whatever we like. But before that, let me first give a name to those sequences yn and zn for which the reconstruction formula hold. So assume that xn is a frame for H, then we say a sequence yn in H is an alternative dual associated with xn if x is equal to a sum of xn multiplied by the inner product of x and the yn for all x in H. And on the other hand, we call the sequence zn a synthesis pseudo-dual associated with xn if we can write x as the sum of zn multiplied by the inner product of x and xn for all x in H. So in general, these two notions are not equivalent, but if they are Bezold sequences, then these two notions are equivalent. So let me give you a quick examples. So once again, let me use en to denote an orthogonal basis for H. Then we can consider the frame xn by duplicating E1 3 times, E2 3 times, and En 3 times to get the frame. So this is a frame with upper frame boundary and the lower frame boundary as well. And then we can consider the sequence yn by defining yn to be E1, E1, negative E1, E2, E1, negative E1, and E3, E1, negative E1, and so on. So we can show that under this definition, this sequence yn satisfies x equals to the sum of yn multiplied by the inner product of x and the xn for all x in H. But the thing is, when we interchange the position of xn and yn and put x equals to E1 into this reconstruction formula, we can see that we get E1 plus E1 minus E1 plus E2 minus E2 plus E3 plus E3 and so on. So this series doesn't even converge in the norm of H. So that means that this sequence yn is a synthesis pseudo-dual associated with this frame xn, but it is not an alternative dual. So which give us an examples that these two notions are not equivalent. So finally, let me introduce another sequence that is associated with xn, which is particularly important, the so-called canonical dual frame. So assume that xn is a frame for H, then we know there exists a frame which we denote by xn tilde. And we call this sequence the canonical dual frame associated with xn. And the canonical dual frame associated with xn satisfies x equals to the sum of xn multiplied by the inner product of x and xn tilde. And if we interchange the position of xn and xn tilde, we still get the reconstruction formula. Okay, I think now we are ready to move on to the second section and talk about the main topic today, the unconditional convergence of frame series. Okay, so we already seen in the previous slides that if xn is a frame for H and yn is an alternative dual associated with xn and zn is a synthesis dual, then we have the following reconstruction formula for every x in H. But thing is, these two sums may just converge in the norm of H. They may not converge unconditionally for every x in H. So that means when we permute the order of xn, we may lose some of these nice sequences yn and zn. So of course, we want to see if there exists some frames such that this reconstruction formula converges unconditionally for every alternative dual and every synthesis pseudo-dual and every x in H. And we briefly mentioned that this is not possible for every frame. So let me first give a counterexample to the following question. So must the series in reconstruction form that converge unconditionally for every yn and cn and x in H? So the way we construct the counterexample is, once again, let me use en to denote the orthonormal basis, and then we can consider the frame by duplicating E1 3 times, E2 twice, and E3 twice, and so on. Then we can define yn to be y1 equals to E1, and y2 equals to E1, and y3 equals to negative E1. And for n greater or equal to 2, we set y2n to be 1 over square root of n E1 plus 1/2 En, and the y2n plus 1 to be negative 1 over square root of n E1 plus 1/2 En. So under this definition, we can show that yn is both an alternative dual and the synthesis pseudo-dual associated with xn. But the thing is, for x equals to E1, we can see that the sum of xn multiplied by the inner product of E1 and the yn is equal to E1 plus E1 minus E1 plus 1 over square root of 2 E1 minus 1 over square root of 2 E1 plus the other terms. And we can see that this inference sum converges conditionally, because when we change the negative sign to positive, then we get a divergent series. So that means this infinite series converges only conditionally. So we just established a counterexample for the case of alternative dual, but we still need a counterexample for the case of synthesis pseudo-dual. And note that the sequence yn we constructed here is both an alternative dual and a synthesis pseudo-dual associated with xn. So to find a counterexample for synthesis pseudo-dual, we need the following lemma. So here's the lemma. So assume that xn and yn are two sequences in H, then this lemma says the sum of xn multiplied by the inner product of x and the yn converges unconditionally for every x if and only if we interchange the position of xn and the yn, we still get unconditional convergence for every x. So because the counterexample we just constructed, we know there must exist some element v in H such that v equals to the sum of yn multiplied by the inner product of v and the xn converges conditionally. And because the yn we constructed in our counterexample is also a synthesis pseudo-dual, so that being said, this yn also gives us a counterexample for the case of synthesis pseudo-dual. So that being said, it's not realistic to expect every frame has an unconditionally convergent reconstruction formula for every alternative dual and every synthesis pseudo-dual and for every x in H. So of course, natural follow-up question is, for which frames xn do we have unconditional convergence of the series in reconstruction formula for every alternative dual yn in x in H? And similarly, we can ask the same question for synthesis pseudo-dual. So in the following, we are going to answer this question and to find those frames such that the corresponding reconstruction formula converges unconditionally for every alternative dual and every x in H. But before that, let me introduce some terminologies. So we say a sequence En is a Riesz basis for H if it is topologically isomorphic to an orthonormal basis for H. So what do we mean by topologically isomorphic is that En is the image of some orthonormal basis under a bounded bijective linear operator. And we say a sequence Xn is a near-Riesz basis for H if there exists a finite subset F of the natural number such that the removal of this F from N leaves us a Riesz basis. So that means that a near-Riesz basis is a Riesz basis plus at most finitely many elements. So let me point out some relations between frames and the Riesz basis and the near-Riesz basis. So a frame is a Rie spaces if and only if it does not contain any redundant elements. And what we mean by redundant element is that the removal of these elements are still preserve the completeness of the frame. So a frame is a near Rie spaces if and only if it contains at most finitely many redundant elements. So that's the relation between frames and the Rie spaces and the near Rie spaces. Okay, so now I believe we are ready to present our main result. So here we go. So if Xn is a frame for H that contains at most finitely many zeros, then the following statements are equivalent. So statement A, Xn is a near Rie spaces, and statement B, for any alternative dual Yn, the series Xn multiplied by the inner product of X and Yn converges unconditionally for every X in H. And similarly, for any synthesis pseudo-dual Gn, the series Gn multiplied by the inner product of X and Xn converges unconditionally for every X in H. So let me first emphasize that the condition that Xn contains at the most finitely many zeros is here because we just cannot get the implication from B to A and from C to A if Xn contains infinitely many zeros. Because for near Rie spaces, the frame has to contain at most finitely many elements. But even if Xn is a frame that contains infinitely many zeros, we can still get the implication from A to B and from A to C. Okay, so now let's see how to prove this result. Okay, so let me first prove the direction from A to B and A to C. So that is, assume that Xn is a near Rie spaces for H, then we know we have to show that for any alternative dual and any synthesis dual, the corresponding reconstruction formula must converge unconditionally for every X in H. So one thing we have to know before the proof is that assume that Xn is a Bessel sequence in H. Then the sum of Cn times Sn converges unconditionally for whenever this sequence Cn is in literal 2. Also, let me emphasize that we usually use this bracket to denote a sequence of element in H, and whenever we use this parenthesis, then that means the sequence must be a sequence of scatters. So now we know if Xn is a Bessel sequence, then this infinite sum converges unconditionally whenever Cn is in literal 2. So let me go back to previous slide for just a second. So if Sn is a near Rie spaces, then of course it is a Bessel sequence. So if we can show that Yn is a Bessel sequence, then it means the inner product of X and Yn must be in literal 2. So of course this infinite series must converge unconditionally for every X in H. And similarly, if we are able to show Zn is a Bessel sequence, then because Xn is a Bessel sequence, then the inner product of X and Xn must be in literal 2 as well. So this infinite sum must converge unconditionally for every X in H as well. So that being said, our goal is to show that for near Rie spaces, every alternative dual and every synthesis dual is a Bessel sequence. Okay, so now because Xn is near Rie spaces, so we know for some k, Sn must be a Rie spaces for n greater than k. And let me use Sn tilde to denote the canonical dual frame associated with Sn for n greater than k. And in this case, Sn tilde is also a Rie spaces. Now, let me fix an element X in H and an alternative dual associated with Xn. And then because of reconstruction formula, we know we can write X as the sum of Xn multiplied by the inner product of X and the Yn from k plus 1 to infinity, and plus the sum from n equals to 1 to this k. But the thing is, we know for n greater than k, Sn is Rie spaces. So that means we can further rewrite those Sn when n is between 1 and k as a sum of xn for n greater than k. So this allows to combine and merge these two sums into a single sum. And where the coefficient is equal to the inner product of x in the yn plus the sum of the inner product of xj and the xn tilde multiplied by the inner product of x in the yj from j equals to 1 to k. And note that xn for n greater than k is a Riesz basis. So these coefficients in the parentheses must be unique in the sense that they must be equal to the inner product of x and the xn tilde. So this gives us a way to relate the inner product of x and the yn to the inner product of x and the xn tilde. And from here, we can show that yn is a Bessel sequence. And similarly, use a very similar technique, we can also show that every synthesis pseudo-dual associated with the near-Riesz basis is a Bessel sequence. And this complete the implication from A to B and A to C. And actually, since an alternative dual is a frame if it is a Bessel sequence, so what we really showed is that every alternative dual and also every synthesis pseudo-dual of a near-Riesz basis is a frame for H. Okay, so now let's move on to the implication from B to A and C to A. So what we have to prove is that assume that Xn is a frame for H that contains at most finitely many zeros, then and assume that for any alternative dual Yn, the series Xn multiplied by the inner product of X and Yn converges unconditionally for every X in H, or for any synthesis pseudo-dual Zn, the series Cn multiplied by the inner product of X in the Xn converges unconditionally for every X in H. Then we have to prove that Xn under this assumption must be a near-Riesz basis. Okay, so our idea is try to prove by contrapositive. So that is, suppose Xn is not the near-Riesz basis, then can we find an alternative dual Yn and an element such that the corresponding reconstruction formula converges just conditionally? And can we find a synthesis pseudo-dual Cn and an element such that the corresponding reconstruction formula just converges conditionally? So this is exactly what we are going to do next. Okay, and we can be more ambitious in the sense that we can ask, can we find some element x0 in H and an alternative dual Yn of Xn that is also a synthesis pseudo-dual such that the infinite sum of Xn multiplied by the inner product of x0 and Yn converges conditionally? So if the answer is yes, then because this sequence Yn is also a synthesis pseudo-dual, then by the lemma we presented while we were constructing the counterexample, then we know there must exist some element, let's say V, such that the infinite sum of Yn multiplied by the inner product of V and the Xn converges conditionally. Then this will establish the direction from B to A and C to A. Okay, so now to find such a sequence and such an element x0, we need to appeal to the following theorem. So this theorem was first established by Hilbert and then extended by Kazaza and Christensen to a case that the frame contains at most finitely many zeros. So what this theorem says is that assume that Xn is a frame for H that contains at most finitely many zeros, then the following statements are equivalent. So statement A, Xn is a near-Riesz basis. And statement B, if Cn is an arbitrary sequence of scalars, then the sum of Cn times Xn converges if and only if it converges unconditionally. So once again, the condition that Xn contains at most finitely many zeros is that because we just cannot get from B to A if Xn contains infinite many zeros. but we can still prove that if Sn contains infinite many zeros, we can still prove from A to B. Okay, so what this theorem says is that if Sn is not the nearest basis, then there must exist some sequence of scaters Cn such that the sum of Cn times Sn converges to a non-zero element conditionally. So now, because of this theorem, we know if Xn is not the nearest basis, we must have such a sequence of scaters and such that the sum of Cn times Xn converges conditionally. So if we are able to turn this scatters Cn into an inner product of some element, let's say x0, and some sequence that is an alternative dual, which is also a synthesis dual, then we are done. Okay, so this motivates the following question. So for which sequence of scatters Cn can we find a sequence Yn that is both an alternative dual and a synthesis dual, and the some element x0 in H such that the inner product of x0 and the Yn equals to Cn for all n. So let me first give a name to this type of sequence of scatters. So let Cn be a sequence of scatters, then we say Cn is realizable with respect to a plane if there exists some element x in H and an alternative dual Yn that is also a synthesis pseudo-dual associated with Xn such that Cn is equal to the inner product of x and Yn for all n. And here's our main result. So if Cn is a sequence of scatters, then Cn is realizable with respect to a plane Xn if and only if either the sum of Cn times Sn converges to a non-zero element in H or Cn are all zeros. So let's see how to prove this theorem. So if Cn are all zeros, then so in this proof, once again, let me use Sn tilde to denote the canonical dual frame associated with Xn. So if Cn are all zeros, then we can just pick Yn to be the canonical dual frame and pick the element to be the zero element. Then we will have the inner product of 0 and the Sn tilde equals to 0 for all n. So now assume the sum of Cn times Sn converges to some non-zero element, let's say x0. Then we can define n to be the span of x0, and we define the sequence Yn to be the Cn bar over the norm squared of x0 times x0 plus the orthogonal projection of Xn tilde onto n perb for all n. Then under this construction, we can see that the inner product of x0 and Yn equals to Cn for all n. So it remains to show that this sequence Yn is not only an alternative dual, but also a synthesis pseudo-dual. Then this will complete the proof. Okay, so to show this sequence Yn we just constructed is both an alternative dual and a synthesis pseudo-dual, we have to show that the sum of Xn multiplied by the inner product of x and the Yn equals to x. And when we interchange the position of Yn and the Xn, we still get x. So let me rewrite x here as Sn plus Sn perb. And here we use Sn and Sn perb to denote the orthogonal projection of x onto n and the n perb respectively. Then the second term inside the bracket is the definition of Yn, and we can see that this in this inner product cross term vanish. So that being said, we can further simplify this infinite sum and split this infinite sum into two infinite sums. One is the sum of Cn times Sn over the norm of x0 multiplied by the inner product of Sn and the x0 over the norm of x0. So you can see that the first infinite sum is exactly the orthogonal projection of Xn onto n. So that being said, the first sum here is just Xn. And for the second sum on the right hand side here, because xn tilde is also an alternative dual associated with xn, so this second sum is equal to the Sn perp. So that being said, the sum of Sn multiplied by the inner product of yn and the x equals to Sn plus Sn perp, which equals to x. So this shows us yn is an alternative dual associated with xn. And the case for synthesis pseudo-dual is pretty similar. So let me skip the argument. So now we can show that we do find such a sequence yn, which is both an alternative dual and a synthesis pseudo-dual. And we also find an element such that the inner product of the element and the yn is equal to Cn for all n. And this completes the proof. Okay, so what we just showed is that only near-Riesz spaces can have unconditionally convergent reconstruction formula for every alternative dual and every synthesis pseudo-dual for every x in H. So now let me apply our result to give another characterizations of near-Riesz spaces. So that is, let Xn be a frame for H, then we know the following statements are equivalent. So statement A, Xn is a near-Riesz spaces. And statement B, every alternative dual and the synthesis pseudo-dual is a frame for H. And the statement C, there exists an alternative dual or synthesis pseudo-dual which has at the most finitely many redundant elements. And once again, what we meant by redundant element is that the removal of these elements preserve the completeness of the sequence. And we just proved that in the case that Sn does not contain infinitely many zeros, then statement A to C are also equivalent to Xn has an unconditionally convergent reconstruction formula for any alternative dual and any synthesis pseudo-dual. So in the process of proving the direction from A to D, we already showed that if Xn is a near-Riesz spaces, then every of its alternative dual in the synthesis pseudo-dual is a frame for H. And the direction from B to A is quite similar to what we did for direction from B to A. So let me just focus on the equivalence between the statement A here and the statement C. Okay, so what we have to show is that every near-Riesz spaces has the same amount of redundant element as its associated alternative duals. And we already showed that if Xn is a near-Riesz spaces, then every of its alternative dual and the synthesis pseudo-dual must be a frame. So we are going to apply one of the result proved by Buckich and Bailey. And what they showed is that every frame has the same amount of redundant elements as its associated alternative dual frames. So because we already showed that every near-Riesz spaces, for every near-Riesz spaces, its alternative dual and the synthesis pseudo-dual must be a frame. So by the result by Buckich and Bailey, then we know every frame, every near-Riesz spaces must have the same amount of redundant elements as its associated alternative duals. And the proof for synthesis pseudo-duals is similar. So now let me move on to the direction from C to A. So one thing we have to know first is that a sequence contains no redundant elements if and only if it has a bi-orthogonal sequence. So what do we mean by bi-orthogonal sequence is if we say Xn and Yn are bi-orthogonal to each other, then that means the inner product of Xn and Yk equals to delta Nk, where delta Nk equals to 0 when n is not equal to k, and delta Nk equals to 1 when n is equal to k. Okay, so let me use Yn to denote an alternative dual associated with Xn that has at most finitely many redundant elements. So equivalently, that means there exists some k such that the sequence Yn for n greater than k has a bi-orthogonal sequence Yn tilde. So by reconstruction formula, we can see that for n greater than k, yn tilde is equals to the sum of sk multiplied by the inner product of yn tilde and the yk. And because yn tilde is a bifactorial sequence to the sequence yn for n greater than k, so we know we can further rewrite this infinite sum as xn plus the sum of sk multiplied by the inner product of yn tilde and yk. So that means that yn tilde is just a finite dimensional translation of xn. So this gives us the following relation between two sets. So on the left-hand side, we have this sequence yn tilde for n greater than k, and xn from n equals to 1 to k. And we just found that yn tilde is equals to xn plus the sum of sk multiplied by the inner product of yn tilde and the yk. So this shows that the union on the left-hand side is equal to the union on the right-hand side. So now if xn, the frame has infinitely many redundant elements, then that means we can use just a finite dimensional translation to reduce the amount of redundant element that xn has from infinity to just a finite number, which turns out to be impossible. So that means that xn must have only at most finitely many redundant elements, and this establishes the proof. Okay, so now let me move on to the third section about the existence of absolutely convergent frames. So there are two reasons why we want to study this existence of absolutely convergent frames. So the first reason is we try to see if unconditional convergence is the best convergence we can have for frame series. And the second reason is we try to find some ways to classify frames and its associated alternative duals. So we know if we use the criterion, let's say having an unconditionally convergent reconstruction formula for every alternative dual and the synthesis pseudo-dual and every x as a criterion to classify frames, then only near-Riesz spaces can be good frame, which is what we just showed. Okay, so now we do have some criterion to distinguish good frames and bad frames by using this unconditional convergence. So we also want to find a way to distinguish good and bad alternative duals by using, once again, the unconditional convergence of the corresponding reconstruction formula. So that is, we say an alternative dual yn is a good alternative dual associated with xn if x equals to the sum of xn multiplied by the inner product of x and the yn converges unconditionally for all x in H. So we try to find some characterization of these good alternative duals when a frame is given. So this motivates the following question. So assume we have a frame Sn, then for which alternative duals do we have unconditional convergence of reconstruction formula? So here's a known result. So what we know is that if Xn is a frame that is non-bounded below, then the infinite sum of Xn multiplied by the inner product of X and the Yn converges unconditionally for every X in H if and only if Yn is a frame. And similarly, we have the same result for synthesis dual. So that being said, for dual, the only possibility for an alternative dual to be a good alternative dual is it is a alternative dual frame. So for general frames, Stoiber and the Balazs gave the following conjecture, which in some sense help us distinguish good and bad alternative duals if we use unconditional convergence of reconstruction formula as a criterion. So what their conjecture says is that if we have two sequences, Xn and Yn, then the inference sum of xn multiplied by the inner product of x and the yn converges unconditionally for all x in H if and only if there exist two sequences of scalars Cn and Dn for which Cn times Dn bar equals to 1 for On such that and Cn times Xn and Dn times Yn are all Basel sequences. So up to this point, there are some known results regarding this conjecture. So the first result is proved by Fernandez and two other people. What they showed is that this conjecture holds if the sum of xn multiplied by the inner product of x and the yn converges absolutely for all x in H. And for this conjecture, and several equivalent statements were proved by Fernandez and two other people, and Balazs and the three other people. Okay, so let me focus on the first result regarding Stoiva-Balazs conjecture proved by Fernandez. Just a second. So this result says that this conjecture holds if the sum of xn multiplied by the inner product of x and yn converges absolutely for all x in H. So that being said, if we are able to find a frame which admits an alternative dual such that the corresponding reconstruction formula converges absolutely for all x in H, then we can use the conjecture made by Stoiva and Balazs to distinguish good and bad alternative duals. So that is, to be a good alternative duals, there must exist two sequences of scalars Cn and Dn, for which Cn times Dn bar equals to 1, and Cn times Sn and the Dn times Yn are Basel sequences. So this motivates the following question. Do there exist a frame and an associated alternative dual Yn such that x equals to the sum of xn multiplied by the inner product of x and Yn converges absolutely for all x in H? But unfortunately, the answer turns out to be false. So let me first give a name to those frames which admit such an alternative dual. So we say a frame for H is an absolutely convergent frame for H if it admits an alternative dual Yn such that x equals to the sum of xn multiplied by the inner product of x and Yn converges absolutely for all x in H. So here's our result. So unfortunately, there does not exist an absolutely convergent frame for H. And this result is sharp in the sense that for any p greater than 1, we can always find frames xn and an associated alternative dual Yn such that the LP norm to the p of the norm of xn multiplied by the inner product of x and the Yn converges for every x in H. So let me first give an example for the sharpness of this result. So once again, let me use En to denote an orthogonal basis for H. Then let me just focus on the case P is between 1 and 2. So we choose K to be a number which is greater than 2 minus P over 4 times P minus 1. Then we can construct the frame by duplicating E1 just once and duplicating 2 to the minus k times E2, 2 to the 2k times, and n to the minus k times En, n to the 2k times. Then based on this construction, we can show that Xn is a frame, and moreover, the LP norm to the P of the norm of Xn multiplied by the inner product of X and Xn converges for every X in H. So this example shows the sharpness of the non-existence of absolutely convergent frames. And finally, let me show that there does not exist an absolutely convergent frame for H. So what we have to use is the following lemma. So this lemma shows that if we have two distinct numbers P and R between 1 and infinity, then it is not possible to find a topological isomorphism between the closed subspace, infinite dimensional closed subspace of LP to a closed infinite dimensional subspace of LR. Okay, so now assume that Yn is an alternative dual associated with Xn such that the sum of the norm of Xn multiplied by the inner product of X and Yn converges for every X in H. Then we can consider the following analysis operator C from H to L1 defined by Cx equal to the sequence of scatters of the inner product of X and Yn multiplied by the norm of Xn. Then under this definition, we can show that C is a topological isomorphism from H to CH. And moreover, C of H is a closed infinite dimensional subspace of L1, and which leads us to a contradiction. So there does not exist an absolutely convergent frame for H. So that being said, unconditional convergence is in some sense the base type convergence we can expect for frames. Okay, so I think that's pretty much for today's talk, and thanks for listening.
All right, thanks, Pu-Ting. We can all thank our speaker by clicking a button at the bottom, like I'm doing right now, and we'll stop the recording.